At several points in this course, we're going to take the idea of functions that we learned about in algebra class, where y is equal to some function of x, and we're going to expand it to different variations and kick it up a few notches. So this section and this chapter is really our first variation, which is vector valued functions. All right, so before we go do that, let's think about what a typical function looked like. When we were looking at a real valued function of one variable, we would have y equals f of x as the notation. We learned that in algebra class. And that implies that x is our independent variable. So we had one independent variable, and it was x. And we had one dependent variable, which was y. All right, so now we're going to take that to a new level. And you've actually seen a variation on this level before, which is when you're looking at a vector valued function. Instead of x, you actually have t. That should look familiar because we learned about that in parametric equations, right? So you take some parameter t, which is one input, one independent variable, and you can get out two outputs, x and y, or three outputs, or more, right? So I should put a little etc. here because you could do it with 4, you could do it with 5, right? We're at our mental capacity imagining what 3 dimensions looks like. We don't know what 5 dimensions looks like. We just know that mathematically we could do it. All right, so let's look at vector valued functions in 2 space, right? In the 2-dimensional space, so that would just be x and y. So given the vector valued function, r of t, which is equal to the vector 4t comma t cubed plus 1. Find r of 3. Okay, so r of 3, we're going to put in one value as our input, and it's a scalar, right? So we're going to take one scalar input, and we're going to receive two outputs, because wherever there was a t, I'm going to put 3. So that would be 12, and that's 27 plus 1, so 28. There we go. So our output has 2 components, and it's a vector, right? So this output has 2 components. All right, so let's practice that again. So we want to find r of pi over 3 given r of t is this vector, or excuse me, this vector valued function, which is cosine of ti plus sine of tj, which is also a vector. All right, so r of pi over 3 would be the cosine of pi over 3 I plus the sine of pi over 3 j. The cosine of pi over 3, draw a quick little unit circle here. Pi over 3 is up here. So its cosine is a half, and its sine is the square root of 3 over 2. Aren't we glad we have the unit circle memorized? There we go. And if you like, you could write that in bracket notation, 1/2 square root of 3 over 2. They mean the same thing. So we had one input, which was pi over 3, and we received a vector output with 2 components. So a 2-component vector is the output. So if this is looking familiar, it should. It's very closely related to parametric equations that we studied in Calculus 2. I actually learned them in pre-calculus, but that was a long time ago. So there is a slight difference in how we interpret this output, but a lot of what you learned in terms of parametric equations is still going to be true here. So let's compare parametric and vector values. You can see the slight difference here. So if we write a parametric equation, that represents this function and evaluate it for t equals 1 and interpret the result. Okay. So there's a lot of ways, if you remember, that you can write parametric equations for a particular function. Lots and lots and lots. Infinitely many, as a matter of fact. The easiest way to write a parametric equation is to just let x be t, and then y will be 4 minus, instead of x, you'd write t. And that would be for negative 2 is less than or equal to t, which is less than or equal to 2. So those three components are writing the parametric equation that represents the function. And again, there's nothing special about t. I mean, you could do t over 3. You could do 5t. You could do all sorts of things. There's infinitely many ways to do this. Now you're going to evaluate this for t equals 1 and interpret the result. Okay, so let me do that over here. So we're going to evaluate. So for t equals 1, x would be 1. Y would be 4 minus 1 squared, which would be 3. So the interpretation would be at 1 second, because usually we assume t is time, right? So at 1 second, the object, oops, I just was about to write that wrong. Object is located at 0.13. All right, so now how does that change for a vector valued function? All right, so the vector valued function, you write it in a different format for starters. It's in a vector notation. But honestly, the rest of it's kind of similar. So you put the t right here, you say let x be t, and then 4 minus t squared, like that. And again, you would also note there's lots and lots and lots of ways to do this. So many ways. And then we would want to restrict our t. So negative 2 is less than or equal to t, which is less than or equal to 2. Right, so it's written in vector valued function notation. All right, now what about evaluating it? Well, evaluating it at t equals 1, then it becomes r of 1, which is a vector, 1, comma, 3. Now notice 1 is in my domain, so we're okay with this. So the interpretation would be at 1 second, the vector is pointing to the point 1, 3. It's a vector, not a point, right? It's not a dot. It's a vector going from the origin to that dot. And that's only if it's in standard notation. Of course, vectors are free, so it can move all around the grid if you wanted to. We just usually don't draw it that way. All right, so let's compare and contrast the original function, which is algebra, right? So in algebra, we learn what 4 minus x squared looks like, right? We know what 4 minus x squared is. It's a parabola. Right? It's a parabola. It has a y-intercept of 4, and then it points down, right? And we're restricting from negative 2 to 2. So we're actually going to stop right there. Right, so this is y equals 4 minus x squared, where negative 2 is less than or equal to x, which is less than or equal to 2, is our domain. If you remember that term from algebra class. Sorry, my parabola is a little wobbly. Okay, now, in parametric form, it went a little differently. So you'd say x equals t, y equals 4 minus t squared. So it has the same shape, but it has direction. So negative 2 is less than or equal to t, which is less than or equal to 2, means that it's going to move this way. Let me show you in Desmos. Okay, so here's the basic algebra function. I graphed it in Desmos so you can see it. And it's right there. It goes from -2 to 2. You can look at it, right? I'm telling it to restrict itself. And it's just static. It just sits there. It's fine, right? There's no problem. Okay, so I'm going to turn that off now. And I want to draw the parametric equation. Matter of fact, I'll leave it on for a second. And I put this parametric equation on. So the parametric equation is the purple one. And you can see that it carves the same path. So it follows the track that the algebra function lays out, but it's parametric, so it has motion to it. It has direction. And just on a side note, I just wanted to mention, remember that you can define parametric forms different ways. So there's the one that I just did, which is the one that we had on our paper. It's t comma 4 minus t squared. But I said there's lots of ways you can do that. So here's some others. The red one is slower because what I did was I divided it by 2. So you can see how slowly it climbs as compared to the purple. And the green is faster, but they're all carving the same path, right? They're all using that same algebra parabola, and they're all following it, but they follow it at different rates because it all depends on how you define your parameters. So that's just 3 different ways that I could define that parametric function, and all it does is it doesn't alter the path, it alters how quickly you move through the path. But nevertheless, the point for the notes is that there's motion to that graph, right? And that was new. Parametrics add this motion piece. Okay, so now what about for a vector valued function? Well, the path again is still here. It's still that parabola. But instead of thinking of it as the parabola, I mean, you do think of it as that, but then you also think of it as you start at the origin and you have vectors pointing all along. So it has motion in it as well, just like the parametric one does. But it has motion because the vectors are pointing to the different places along that path. So this is r of t equals t comma 4 minus t squared. And again, from -2 to 2. And the last comment to make about this is actually on the top of the next page. It got snuck over there. So we're going to, as a convention, include the orientation. That means these arrows. So the orientation is the arrows when we're graphing a vector valued function, because it's essentially a glorified parametric, right? Right, but we're only going to plot the points because those are the tips of the vectors. We're not going to plot the vectors themselves because that would just clutter up our graphs to be filling them with vectors constantly. I mean, even though that's technically what's happening. But it would be too messy all the time to draw lots and lots and lots of vectors in.